Okay, so we're going to talk about transition metals and transition metal complexes today. Now, remember, when we talk about transition metals, a lot of them actually you'll see, a lot of metals will find occurring as solid inorganic compounds, and we call those minerals. Okay, and if you hear about metallurgy, metallurgy is actually the science of technology associated with mining relevant ores, okay, and concentrating those ores, and then reducing the ores to pure metals, okay, and then not only reducing it to the pure metals, like we have to purify the metal, and then after we purify the metal, then we can have the exact proportions that we want to mix things up to make alloys. And because we purify it first, by knowing the percentages, we can get the types of physical properties in our alloys that we want. So there's a lot of science to that, because it's not just a composition, it's how quickly you heat it, and mix it, how quickly you cool it, and as you're cooling it, how you work it. So there's the annealing process. When we talk about physical properties of our metals, we have two different forces that we have to work with. Okay, so if you look at the radii, right? If I say 3B, 4B, 5B, that's not B, 6B, 7B, and 8B, if you look on the periodic table, covers several elements, and then 1B and 2B. When you look at the radius, okay, I'm just going to give you a rough draft of what the graph looks like. You look at the graph, what you'll find, okay, in period 4, you'll see a decrease all the way down to 6B, goes up with 7B, and then it goes back down again, and then starts increasing up. And then this is period 4. Alright, and then period 5 and period 6 all have similar trends, where they start here and they just go up. Okay, so this is period 5, and then period 6 is similar but higher up. Okay, and the reason that they show your change in radius as we go across is that we have two opposing forces with it. Okay, so one is that you're going to have a contraction here. All right, so as you move down, you're in the same. As you move down, what are we doing here? We're filling in basically our orbitals. But then you get to a part where it starts expanding because you have a repulsion. So this is basically a contraction, because if you look at our d orbitals, okay, it's contracting because energetically what's happening is you're gradually filling all those in. Now, as it starts to expand, what's happening there is you're beginning to have a repulsion, okay? Because I have 2 electrons in the same orbital. So having an electron in there is better than having it empty. But then when I start filling it in, then I'm competing between contracting by having electrons in my orbital and having the repulsion by having multiple negative charges in a close vicinity. Now, what else do we know about the physical properties of transition metals? Well, another thing we know about transition metals is that they have multiple oxidation states. Okay, so the highest value we'll see Osmium has 8. So the highest oxidation state, osmium and osmium tetroxide, this has a high oxidation state of 8. Manganese can vary from +2 to +7. So +7 would be like in permanganate. Okay, so basically we see that we have multiple oxidation states in a transition metal. Another physical property is that many are colored. Okay, so a lot of the colors, like if you look at the Himalayan salt, it's very pink, and the reason that the salt is pink is not because of the sodium chloride. It has an impurity in there of manganese that turns it a pink color. Okay, so many transition metals, okay, compounds are colored. Okay, and okay, many of the transition metals and compounds okay, so many of the compounds are colored. Many of the metals and metal compounds have magnetic properties. Okay, so what we're going to do is we already know about the multiple oxidation states. We've been calculating that for quite a while now. We're going to talk about the magnetic properties first, and then talk about colors and the complexes, the compounds, and naming them. Okay, so what are the magnetic properties? We've talked about on the atomic and molecular level about the unpaired electrons. So on the atomic and molecular levels, so like an oxygen gas. Okay, if our orbital have unpaired electrons, they are paramagnetic. They're attracted to magnetic field. Okay, now we talked about oxygen being an example. Okay, but if we look at something like, let's say iron, okay, and we look at let's look at the d orbital. Okay, so what you find for iron, for the 3D, okay, is that iron itself has like the 26 electrons. And it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d what? So 1, 2, 3, 4, 5, 6. Okay. So what we would have is 1, 2, 3, 4, 5, 6. Because iron has unpaired electrons, it is paramagnetic. Okay. Diamagnetic. Okay. So orbitals have electrons, have only paired electrons. Okay, and we were talking about, this is called diamagnetic. And they are weakly repelled. by a magnetic field. Okay. So at times it was considered that it wasn't even responding, okay, to a magnetic field, like it wasn't influenced at all, but it's actually slightly repelled, very, very weakly. And an example of that we've been talking about was if we looked at fluorine, we find out that fluorine is diamagnetic. Okay, now, let's see that. Here we go. So, what about our elements? So if we look at zinc, zinc is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay, just double check that before I'm done. Okay, and when you see this, let me just focus on this one. These are all paired. But the 4s2, 1, 2, 3d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And before the zinc, for my noble gas, it would be argon. Okay. So what this means is that zinc is diamagnetic. Okay, so these are our atomic and small molecular level descriptions of their magnetic properties. But what about bulk properties? So when I talk about bulk properties, we're talking about all of your, let's say, atoms, since we're talking about our metals today, and how they influence each other. Okay? So we also have magnetic properties that depend upon how they influence each other. Okay? So, what happens is this. If I have a paramagnetic substance, what I'm going to do is I'm going to represent each substance is paramagnetic. Then we can represent their magnetic property with an arrow. What happens is in any random substance, they're going to be randomly oriented. Okay? There's no reason that they should be lined up at all. And because they have a random orientation, just because a substance is paramagnetic doesn't automatically mean it's lined up. So this is in the absence of a magnetic field. Okay, so they're constantly changing their spin. But if they all align parallel to an external magnetic field, okay, so I'm going to, sorry, I'm going to make them a little bigger so you won't have as many rows. But what happens is, if I put in a magnetic field, they all line up. Kind of like a compass, right? we've got Earth's magnetic field, and our compass lines up to that. So they're all lined up parallel to this. Then this substance is called ferromagnetic. They all line up in the same orientation. Let me just pull this up a little. Okay? So, when I put an external magnetic field, they all line up to it, then it's ferromagnetic. If I have it in the absence of magnetic field, then they are randomly oriented, but each one has a field because it's paramagnetic. What happens if we do this? Suppose I put in my magnetic field, okay, and they align in opposite directions to the magnetic field, okay, to each other, okay. In other words, when I put in my magnetic field, and this one lines with my magnetic field, then the next one lines against it. And that causes it to go up and down. Okay? And what happens is this. Because they're all the same substance, so they all have the same small paramagnetic field, they cancel each other out. So, they cancel, all right, each other. And we call that anti. All right, you see that? Anti-ferromagnetic. So, a substance might contain atoms that are paramagnetic, but because when I put in my external field, they will align in opposite directions and cancel each other out, it won't display magnetic properties. This is then said to be anti-ferromagnetic. Okay? What happens if they align, but they're not the same magnitude? So, let's say they alternate. All right. One second here. So, when they alternate, okay, this is what happens. They align in opposite directions. To each other, right? But they only partially cancel each other out. Okay, then this substance is said to be ferri, with an I, magnetic. Okay, so ferromagnetic is a bulk property where they only partially cancel each other out. Anti-ferromagnetic is they completely cancel each other out. And ferromagnetic, they all align in the same direction, and they enhance their magnetic properties because of that. So those are the bulk properties for the magnetic properties that we're talking about. Okay, so let's move on. Let me just, actually before we move on, let me just give you the different terms. On the molecular atomic or molecular basis. We have paramagnetic and paraelectron. Okay, diamagnetic, all electrons are paired. Okay, then we have bulk properties. That is we're now talking about only the paramagnetic compounds, and they all align with my magnetic field. It's called ferromagnetic. If they alternate in alignment, and cancel each other out, cancel out completely, this is called anti-ferromagnetic. Okay, and finally, if they alternate in alignment, but only partially cancel each other out. This is called ferri, with an I, magnetic. Okay? Alright, what we're going to do now is move on to transition metal complex.